Hello and welcome to another video from Ellensburg Amplifier Repair and Service. My name's Todd, and here we have part 2 of this American Bass VFL1100.1 of the power supply. I have spent numerous hours rebuilding what has been previously done, so there was quite a few errors in the previous repair attempt. So I'm going to just try to go over this briefly here on what I have done to resolve the issues of this board. So originally, as you noticed in part 1 of this video, which I will have right up here in the corner, that the gate signals were off, not significantly, but just a little bit. So what I did is I replaced the Zener diodes and the signal diodes to the 2 transformers that were off just a little bit, which the Zener diodes brought that gate signal back down to relatively where it should be, within 1/10 of a volt. So the 2 transformers now are proper on their gate signals. And so what I did is I went through and refitted all the IRFP064N transistors in the power supply, as you can see here. I checked for drain source shorts anywhere. I checked for gate to drain shorts anywhere. You'll find solder bridges typically between gate drain or drain source from the bottom side of the board when you're soldering these in. And it'll just make that transistor heat up significantly when you're trying to switch it. So I got those all in, and then I had to replace the capacitors. It's right on their side. Sorry guys, you can't see that, but there's 2 Mylar capacitors here for your snubber. I had to replace those. Those were the wrong values, and I had to replace 1 resistor here, which was the wrong value, which I may have covered in part 1. I'm not 100% sure on that. So I got them all in, and then I went to fire up the board, and I had 1 transistor heating up, a single one, over here next to this probe. And I couldn't, it took me a minute, but I couldn't figure out why it was heating up. I double checked, made sure I didn't have any solder bridges. So typically when a transistor heats up, when it's trying to switch that drain source on and off, and it heats up, that means there's going to be either excessive load or a short on your drain source somewhere. And I did all my measurements, and I couldn't read a short. And I was like, oh my gosh, I'm getting confused on why it wasn't reading a short, but it was heating up like it was shorted. Well, come to find out that the previous tech that tried to repair this had the drain of this transistor tied with this drain, and this drain. So all 4 of these drains were tied together to the same point. But if you go back and look at the transformers, how many transistors are on each side of the transformer? So let's count those. So 1, 2, 3, 4, 5, 6. And how do I know that? Because right here's a division which separates this bank here from this transformer, and this bank here is this transformer. So you have 1, 2, 3, 4, 5, 6 transistors per transformer. So if you know how transformers switch, you're going to have 2 halves to a transformer. One half will be on, the other half will be off. The other half will be back on, the other half will be back off. So it switches back and forth, back and forth. So you have 3 transistors switching one side, and you have 3 transistors switching the other side. And then, of course, you have your common of your transistor tied together. So that's, each transformer has 6. Well, he had 4 of these drains tied to the same point, going back to this side of the transformer. Oh, so when this gate was trying to switch on, it was in essence, switching on when these were switched off. Because this is supposed to switch this side, not this side. Sorry, I don't have, I'm not sure if you can see down in there, but you can kind of see right here where he took some copper wire and just ran legs for the drains for these. So I cut that drain loose, and underneath I ran two 18 gauge wires, insulated wires, from the drain of this over to the bottom side of this transformer. So now these three swing at the same time, and these three swing at the same time. So on, off, off, on. And now this transistor no longer heats up. And I'm assuming he, whoever did this, was using a high current supply, because the transistor that came out of that spot was shorted, obviously because it got hot, because it was switching against the other side, switching at the wrong time. And that goes back to me always saying, the transistors have to switch at the right time. They can't have any noise, overshoot, not a lot of ringing. There's a lot involved with switching transformers, a lot more than you think. So what I have here is I have you can see the scope in the upper left hand corner there. I have 3 channels hooked up. I've got a positive rail channel hooked up, a negative rail channel hooked up, and then I have a channel hooked up to the snubber of this transformer, because this transformer here is the main area of concern when it comes to reliability. Now, don't be alarmed. There you can see that there's 5 capacitors here and 3 here. The total capacitance of this is the same as this, so don't be alarmed here. At first I was looking as like, oh my gosh, he's got the wrong value of capacitors in, but it comes out to be the same total value capacitance wise. So again, I've got a probe on the snubber of the transformer. What I'm looking for is noise. Of course voltage too, but I'm looking for noise. We don't want any noise in this. Noise creates heat. So as you can see, the yellow trace is my 12 volts. I do have the 12 volts hooked up. I'm using my 10 amp current limited supply. It's really quick to detect shorts, so it'll turn off as soon as it sees any form of short. It's really quick. So I like using these brick power supplies. So what I'm going to do is I'm going to go ahead and fire up this power supply, and we're going to be looking at how clean these lines are, because again, we don't want any noise. So let me move the trace to 10 volts of division on the snubber there. So just at the beginning here, I'm just going to pulse this, because it'll slowly charge these capacitors up. As you can see the lines, as I slowly pulse this, you can see the rails build. Up to the proper voltage. So let's go ahead and fire this, and I've already checked with my thermal imaging camera, nothing's heating up. So there is the power supply. So what I'm looking for is the snubber. You can see that square wave has almost practically 0 overshoot or undershoot on that. That is a good square wave signal for a snubber network. If you had any odd issues, you will see it right there. Now, the purple line, the line on the top, is my positive rail, and then I have my negative rail. And as you can see, there is absolutely 0 noise on the rails itself, and that is what we're looking for. Now these rails are charged. So I'm about 145 volts, as you can see there, for the rails. So now do the math side by side. If you're to add up the two sides of the rails here, you have what? 280 volts potential on this amplifier. And even currently right now, there are some discharge resistors right out of view. Right here, there you can see a discharge resistor. Those are responsible for discharging your rails. So it's a 10 kilo ohm. 10 kilo ohm, yes, 10 kilo ohm. So it'll slowly discharge it. I have my scope on the just triggered once on the single, so I can keep that picture up on the screen there, because I don't want these rails to stay running and have that high voltage potential. So I just wanted to charge it, read the signal, and then let it drain. Because what's my rule of thumb, guys? These rail voltages here will absolutely give you a bad day. Keep your fingers out of that. The DC potential on this is, on these big amps, they're astronomical. So stay safe, keep your fingers out of that. So that is my primary goal of this power supply, is clean sine waves, no overshoots, no undershoots, no ringing. And then the rails, excuse me, the rails, no noise. So this power supply is good to go back in the board. Let me turn the power off on this. And that's really what I have done for this. I'm going to do some fiberglass epoxy work down here to strengthen this board up. This is the original board that the other tech had put in. So I'm going to reinforce that board. And since everything's together and everything has a clean sine waves, clean signals, none of the drivers heat up, I do believe I'm able to put this back together. So hopefully you guys have learned something on this. Again, if you have any questions, please feel free to leave the comments down below. I'm always more than willing to help answer questions. I'm a pretty busy person, so give me a minute to respond to you when I can. But otherwise, I'm here to help you guys. I hope you guys have learned something on this. And again, keep your fingers out of the rails. Stay safe, guys. We'll catch you on the next one.